Welcome to this explainer. Today, we're doing something absolutely fascinating. We're going to literally open up the black box of large language models. We hear about these massive AIs every single day, right? But how do they actually process language? What is the mathematical magic actually happening under the hood? Well, let's dive right in and map out the exact journey a piece of data takes as it travels through the architecture that changed the world, the transformer.
The true art of memory is the art of attention. That's a quote from the great essayist Samuel Johnson. And get this, it's from 1759. He was talking about human psychology, obviously, but he accidentally hit the nail right on the head when it comes to cutting-edge AI. It turns out that for an AI to remember context, to grasp nuance, and to actually generate coherent text, it needs a mathematical mechanism for attention.
So, that brings us to the core question for this explainer. How does AI actually read and write? To demystify all this complex math, we're going to follow a single protagonist on a journey. We'll start on the ground floor, right where raw text enters the system, and travel all the way up to the penthouse, where a brand new word is finally born.
So here's our roadmap. 1, we'll meet the transformer. 2, we'll prepare the input. 3, we dive into the power of attention. 4, we step inside the transformer block. 5, predicting the next word. And finally, 6, we'll look at scaling and fine-tuning.
All right, part 1. Meet the transformer.
Now, before we can even think about building a language model, we need raw material. Our protagonist on this journey is called a token. You can think of a token as just a fraction of a word or a symbol that acts as the absolute basic unit of data an AI processes. So if you feed the phrase, "thanks for all the fish," into a model, it doesn't read it as one long string of text. It chops it up into vocabulary indices. The word thanks might become, say, token ID 5. This is our starting point. But, a single ID number doesn't actually tell the AI anything about what the word means.
Which takes us to part 2, preparing the input.
To actually give our token some meaning, we have to convert it into an embedding. Think of this as the ground floor of our transformer building. An embedding is a high-dimensional vector. It takes that simple raw token ID and maps it to an incredibly rich mathematical identity. Imagine a vector with 512 or even 12,000 dimensions, and each dimension captures some abstract linguistic feature. So the word chicken gets a very specific mathematical fingerprint, and so does the word road.
But there's a huge catch here. Unlike us, reading a book from left to right, the transformer reads its entire context window all at once, in parallel. It has literally zero inherent concept of word order. So we absolutely have to inject positional information into our embedding. We can use absolute position, which is kind of like placing words on a fixed ruler, or we can use relative position, which calculates dynamic relationships between words later on in the process. Without these positional embeddings, the AI would have no idea what the difference is between the dog bit the man and the man bit the dog.
Okay, part 3. The power of attention.
This is where things get genuinely exciting. Our token is about to enter the multi-head attention layer. I like to think of this as a very mathematical cocktail party. Let's say our current token is the word it. At this party, it acts as a query. The query is basically asking, hey, I'm a pronoun. I'm looking for a noun to attach myself to. Who's out there? Then all the preceding words, like chicken or road, they act as keys. They're holding up little name tags indicating what they're offering. We calculate the dot product between the query and the keys, which gives us a similarity score. If the query for it heavily matches the key for chicken, boom, a connection is made. Finally, the chicken token passes along its contextual meaning back to it as a value. The model mixes these values together, and suddenly it mathematically contains the essence of the chicken. And because this is multi-head attention, the model is running dozens of these parties simultaneously to find all sorts of different semantic relationships at the exact same time.
But wait, there is a very strict rule at this party. When we train these causal left-to-right models, we have to prevent the AI from cheating. Think about it. If the AI is trying to predict word number 4, it definitely shouldn't be allowed to peek at word number 5. So we apply a mask over all the future words in the sequence. We mathematically set their scores to negative infinity, and when the math runs, negative infinity turns into a probability of exactly 0. The future is completely hidden, which forces the model to genuinely learn how to predict context.
Moving right along to part 4, inside the transformer block. So the attention mechanism we just went over is actually housed inside a much larger structure, and it operates a bit like a conveyor belt. We call this conveyor belt the residual stream. Our token travels up this stream.
First, it goes through a layer norm to keep the math stable, preventing the numbers from getting too crazy. Then, it hits that multi-head attention cocktail party we just talked about. This is the only place where tokens actually talk to each other and mix information. Next, and this is crucial, we add this new enriched information back into the original residual stream. We don't overwrite the token at all. We just seamlessly add context to it. Finally, it passes through a feed-forward network. That's just a standard neural net layer that processes this new info independently for every single token. And this cycle, it repeats over and over again through dozens of stacked transformer blocks.
All right, part 5, predicting the next word.
We finally reached the top floor. Our token has traversed the entire network, and we hit the language modeling head. The AI looks at its vast vocabulary and assigns a probability score to every possible next word. But how does it actually choose? Well, if we use greedy decoding, the AI just picks the single most probable word. Period. It's safe, sure, but honestly, it can be super boring and repetitive. If we want that creative, human-like text, we use nucleus sampling, also known as top P. Instead of just grabbing the top word, we dynamically sample from a pool of words that make up the top percentage of highly likely words. This lets the AI occasionally pick a slightly less obvious word, giving the text life, diversity, and that spark of unpredictability that reads like a real human actually wrote it.
Okay, so we've tracked a single token's journey. Let's head into our final section, Part 6, Scaling and Fine-Tuning.
405 billion. Just let that number sink in for a second. That is the number of parameters in Meta's Llama 3.1 model. The journey we just went on, the matrix multiplications, the cocktail party of queries and keys, all of that happens across 405 billion parameters, in parallel, practically instantly. The sheer engineering scale required to pull this off is just breathtaking.
And that massive scale brings us to scaling laws. Researchers have found that AI performance is strictly dictated by 3 main pillars: model size, which is how many parameters we have; dataset size, the raw terabytes of text we feed it; and compute budget, meaning how many supercomputers we can actually keep running. If you increase these 3 variables, the error rate goes down, and the AI gets smarter, following a highly predictable power law curve.
But as you can imagine, running models this giant is incredibly expensive, so engineers use clever tricks. Enter the KV cache. When an AI generates a long paragraph, it does it one word at a time. It would be incredibly wasteful to recalculate the keys and values for the entire paragraph every single time we just want to generate one new word. So we cache them. We literally store the answers from the previous cocktail parties right in memory. This saves immense computation time and is exactly what allows these giant models to talk back to you in real time.
Now, what if we want to teach this massive 405 billion parameter model a new skill, like reviewing medical documents? Retraining the whole thing from scratch is way too expensive. That is where PEFT comes in, parameter efficient fine-tuning. Using techniques like LoRa, we freeze the massive main model and just train tiny, specialized layers on the side. We basically bolt on a small, cheap module that heavily influences the math, giving the AI brand new domain expertise without the billion-dollar price tag.
Which leads us to one of the most fascinating frontiers in this entire field: in-context learning. Sometimes you don't even need to fine-tune the model at all. You just give it a prompt with a few examples, and the model magically learns to perform a brand new task on the fly while it's actively processing your text, without any permanent updates to its parameters whatsoever. It's literally learning just by reading your prompt.
So how is this even possible? Well, one leading theory from the field of mechanistic interpretability points to something called induction heads. Researchers have found these abstract circuits forming inside the attention layers, and these circuits look for patterns. If they see an A followed by a B earlier in your prompt, and then they see an A again later, the induction head acts like a copying machine. It says, I know this pattern, B comes next. It's essentially pattern matching on steroids, allowing the model to adapt to your specific logic instantly. So we've traced the math from a simple token all the way up to incredibly complex pattern recognition. But I want to leave you with a final kind of provocative thought. We built the transformer, right? We wrote the equations for queries and keys. But circuits like induction heads, the model formed those entirely on its own during training. If we don't fully know all the mechanics of how they learn in context, what else might these networks be teaching themselves inside the black box? Thanks for joining me on this explainer. Keep learning, and I'll catch you next time.